Hello once again. Now we're going to continue talking about spatial data alignment, and we are going to talk about a set of data that was acquired by Lauer Peralta, and Lauer is working in Bella, and he's been working in the region where I was raised, and it's in the southeastern part of Buenos Aires, approximately 4 hours to the south. And these formations, they're called sierras, and this place is called El Volcán. It's a very productive place, and it's been focused on agriculture for a long time. This region has been working in agriculture for approximately 50 years, and they have these horizons in the soil that's called Tosca. So the work that Lawel has done has tried and manually measure the depth of the soil. So they use a tool to see how deep the soil goes until there's rock. So we'll be talking about this example to continue our conversation on how to combine data. So let's suppose we want to map the soil depth at the field. So we go to the field and we measure this attribute by using manual measurement systems that are very tedious and slow. And we cannot sample every part of the field this way. So we did our best effort and we got our sampling points trying to cover all the zones of the lot of the plot. We also have some idea that we've collected that are covariables from the soil and the landscape by using less costly methods. That is to develop a model that is based on this auxiliary data in order to map the soil depth with more accuracy. So that's the main objective. So on the one side, we have this sample that's made by hand, where the tools are used to measure the depth of the soil when there's more than 150 centimeters. Let's say that that's the maximum depth. But the other way to do it, the variable is called a hard pan or H-pan. H-pan, you can see it here. And then we have other variables that are topographic variables that derive from doing measurements with a rake that measures electric conductivity, and it's a covariable of the soil that's very useful for many different problems related to precision agriculture. So we have these two sets of data, and we're going to try and see if they are properly read. And this data, the first thing that we have to do is to make sure before anything that the projections are correct. And by doing this, we can align it. And once we've made sure that that's the case, we generate a map and we can extract the different values of elevation by using the different points. So we've got elevation, and then we have this other variable that's H-fan. And we can see that there's not so much variation in terms of elevation, but you can see it. And we also have the points where the hand samples have been taken. The activity that we want to perform, and I'm going to go back in here, is to make sure that we can use the picture to extract the values from those points where we've collected these soil samples. So that's the method that we are using. The function to do this in R, it's called extract. There are several ways to do it. The first one is a simple way where the image has pixels and where the tool goes in. The pixel that goes there where the tool is used is the pixel that we choose. So there are several variables that are being seen at the same time. So we're extracting all of those different variables that are in that series of images. They're all in the same data set. And with this expansion that's called, that has a description of the data that we've collected. So this is the way that you diagram this. And head means that we're showing an example of where the tool was used. On the other hand, we have an example where we do another type of extraction that's called bilineal. And that same method requires another extraction method that, apart from having the point where the pixel is, it takes the pixels that are surrounding that main pixel, and those are the closest neighbors. And these are neighbors that have a distribution that looks like a movement of uh, chess pieces. So this method is called bilineal. And there's another method that we're explaining here that consists on doing an extraction by using a buffer. So in this case, you put some sort of arch around the point where you take the sample from, and it includes all the different points that are within that arch. And you can take an average called median. The, the best statistic to get would be the mean, the average. So we have these three different extraction methods for sampling images. And once we understand these functions, let's suppose that we are doing this this function by using the buffer function that I just mentioned. And this is the example. After that, you can build a new data set. And that's when you see that these values have been extracted. So you are going to do a new data set that combines, on one hand, the data that you took by hand and the data that's been extracted by using the average or the mean of the buffer. And this is how a data set would look like, a new data set that obtains what you measured by hand and also different variables that describe the topography. This is a very effective way to create new data. And the upcoming topic is called Space Union, so see you there when you are ready.